Okay, so for the rest of this class, I'm gonna talk about exam two. Okay, so like we said before, exam two will cover chapter oops 5, 6, and 8. Okay, so chapter 5 is about some discrete distributions, right? Chapter 6 is about the continuous distributions, and chapter 8 is about sampling distributions. Okay. Now let's have a quick review of chapter 5. So in chapter 5, first of all, we introduced you the first discrete distribution is called Bernoulli. A Bernoulli distribution, right? Say xi has only two possible outcomes, 0 or 1. So 0 means a failure, and 1 means a success. And it has a probability to get a 1. Okay, so which means it has a probability to get a 0. So this is what we called a Bernoulli random variable. Okay, so it has its own, PMF because it's discrete, right? Its possible values or 0 or 1 will be 0 or 1, right? And also you need to know is expectation variance, right? So based on this, we had another distribution called binomial distribution. So for a Bernoulli distribution, it has only two possible outcomes, either a 0 or 1. But for a binomial random distribution, actually it repeats, like it has a n such Bernoulli random variables. Say x is the binomial random variable, actually is the summation of n such Bernoulli random variables. So each is a Bernoulli. Okay, each is a Bernoulli. And also we know that those Bernoulli random variables are IID, which means they're mutually independent and they all have the same distribution, which means they all follows the Bernoulli distribution with the same parameter p. Okay, so what does it mean? It means x is the number of successes within, like in n independent Bernoulli trials. So for a Bernoulli random variable, or for a Bernoulli trial, you can imagine you're tossing a coin with probability p to get a head. So which means the probability of getting a tail is 1 minus p. So here you define getting a tail is a success, right? So a binomial random variable actually is to toss the same coin for n times, okay, for n times. So, and you would like to know, okay, so the number of heads that you can get after n tossing, like, right, in toss, when you toss the coin for n times. So I'm gonna say this x follows the binomial distribution with two parameters, n and p. So n is the number of Bernoulli trials, and p is the probability of getting a success for each, Bernoulli trial. Because all those xi's, all those Bernoulli random variables have the same distribution, right? So the p's should be the same, right? Okay. And also we can write down the PMF, right? Which is equal to this. This should be the small p. Okay, so n is a constant, p is a constant, right? They are all parameters, unknown constants. Like sometimes you will know it, but like in general you won't know it. Okay, So x can be equal to 0, 1, 2 until n, right? Because you just toss this coin for n times. So the uppercase, the upper limit should be n. And you can have the corresponding expectation, and you have the corresponding variance, right? And make sure you know how to derive them, right? Make sure you know how to derive them, like using the information of Bernoulli random variable, okay? Using the information Bernoulli random variable. Okay. Now we have introduced to you the binomial random variable and the Bernoulli random variable. And after that, we learned the third discrete distribution called Poisson, right? Poisson distribution. Okay, so Poisson distribution actually counts the number of arrivals or the number of occurrences within a sampling unit. So this is important. Remember in class, we changed the sampling unit from a second to 1 minute, or from a minute to a second, or from a minute to an hour, from an hour to say a week, right? You can also change your unit from say an area to another area, right? Okay, so I'm gonna write down the the PMF, right? The PMF of a Poisson is equal to this stuff. So x is from 0 to infinity. Okay, just remember, even if x goes to infinity, right? Poisson is still a Poisson random variable is still discrete. Okay, just remember in chapter 3, like we learned how to figure out whether a random variable is discrete or continuous, right? It does not depend on whether it's is countable or not. Sorry, it depends on whether it's countable or not. It does not depend whether it's infinity or finite. Okay, it really depends on whether it's countable or not. Okay, and also we know that it has a property that expectation is equal to its variance is equal to this lambda. So we call this lambda as the rate parameter. Okay, so that's the Poisson distribution. Remember, Poisson starts from 0 to infinity. Okay, so that's all for chapter 5. So in chapter 6, we learned some other some continuous distributions, right? We learned the uniform distribution. Of course, this refers to the continuous uniform distribution because the discrete uniform distribution was pretty easy, right? It's like the probability to get a number when you really die, right? But for a continuous distribution, uniform distribution, it will be like this. Say it's defined on an interval from A to B. Okay, so this is the PDF of a continuous uniform distribution. Okay, so it's will be like this. So speaking of the continuous uniform distribution, I think we have derived all of these properties in sample exam 1, right? But from like for exam 2, I'm not gonna give you the sample exam again because it's gonna be different from the previous steps, and since we need to stay at home, and you have a day to finish this, so like I'm not gonna say okay it's closed book closed notes, right? I cannot like monitor you, so like it really depends on how do you like check those materials. But one principle is that you cannot discuss with anybody else. Okay, you have to do this by yourself, but you can check the notes, you can check the videos. Okay, so this fx is equal to 1 over b minus a when x belongs to a and b, right? And 0 otherwise. And also, you have to know that a and b are constants. Okay. We also know the expectation. this variance divided by 12. Okay, so that's the basic steps for uniform distribution. And again, when you want to calculate the probability of a uniform random variable falls into a specific interval, you can have like two basic ways. The first way is to use the definition, right? Which means you can calculate the corresponding, not the definition, but you know, the very basic tool, like you can use the integral, right, to calculate the corresponding area constructed by, say, you know, the corresponding range and this PDF, okay? And because this distribution is pretty special, so you can also use the geometric methods, some geometric methods. For example, so A is equal to 1, B is equal to 2, and you like to calculate the probability that, say, X falls into this interval, right? So basically, in this example, this is 1.5, right? So this is the area that we like to calculate. So instead of using the traditional integral method, you can also use the geometric method, right? So because this length is equal to 1. So in order to make the whole area to be 1, your height should be equal to 1, right? So which means the height of this square, of this rectangle, is 1, and the length is 0.5, right? So 0.5 by 1 is 0.5, which is pretty easy. Okay, so that's the continuous uniform distribution. And after that, we also learned normal distribution, right? Normal distribution. So this is one of the most important distributions of all time. Why is that? Because we have discussed many aspects before. Say, in general, there were a lot of stuffs in reality. They can be measured using a normal distribution. Say the blood pressure, right? The height, the weight. There were a lot of stuffs, okay? And also there is another important reason that normal distribution is the most important distribution, because of the CLT, right? No matter what kind of original distribution X is, right, you will always have its sample mean follows a normal distribution when n is large. Okay, so based on this, we're gonna have, you know, the confidence intervals in chapter 9. The confidence intervals for the parameters, and also we can do some hypothesis testing. Hypothesis test. Okay, they're all based on the central limit theorem, like in general. Okay, so that's the main reasons that the normal distribution is that important. Okay, and speaking of normal distribution, you have to know that this distribution is a bell-shaped curve and symmetric with respect to its expectation mean, right? So X follows a normal distribution with mu and sigma squares. So two mu and sigma squares, so two parameters, right? So mu decides its location, and sigma decides its width, the average width, which is the spread of the data, right? So we call this one the mu as the location parameter, and sigma square as the scale parameter. And you have to know how to write, you know, the PDF of a normal distribution, okay? And it's pretty hard for us to get a closed form using the integral. To get a closed form of the CDF using the integral, like what we did before, right? So every time when you have a PDF, like you calculate the integral, right, to get a CDF, but well, it's you cannot do this using the same formula. You cannot do this by hand, like to calculate the CDF of normal distribution. So I'm gonna just use this symbol to denote the CDF of a normal distribution, okay? And it has the corresponding properties. So we have discussed this in class. And also, you have to know how to convert a standard, a general normal random variable to a standard normal random variable, right? Which is z. So z is equal to this, right? Okay. Which means this curve is also a bell-shaped curve, but it's symmetric with respect to 0, right? Its expectation is equal to 0, and its standard deviation is equal to 1. Okay, so that's the normal distribution. Also, you need to know how to read the z-table, right? Read the z-table. Okay, and what else? And also, we learned gamma distribution. It has two parameters, alpha and beta, right? We know, we learned is PDF, right? Using the gamma function. So you have to know what is a gamma function and its calculation properties, right? And also you have to know the expectation, the variance of a gamma distribution, okay? And the last continuous distribution we mentioned in chapter 6 is the exponential distribution. Exponential distribution, okay? So exponential distribution, actually for this distribution, we have discussed a lot, which are not listed on the slides, right? So basically, this distribution actually describes the waiting time between two events in a Poisson process, right? Say this is a Poisson process. So the number of arrivals, say, for example, you're counting, the number of phone calls arrived within an hour, right? So those numbers are the number of phone calls you got, right? So those numbers are discrete, right? And say the number of phone calls you got is x. So x follows a Poisson distribution, right? Because it's discrete. And also is the number of arrivals, the event of arrivals. Okay, so it follows a Poisson distribution. But within every two events, between every two events, we have a waiting time, right? The waiting time. So the waiting time, say between the second and the third, follows a, let's say t. Okay, so this t is not the t distribution. Okay, it's the time. It's a random variable. Okay, so this t should follow an exponential distribution with parameter beta, and this beta actually is just 1 over lambda. Okay, so you can see sometimes people say follows an exponential distribution with parameter lambda. So this lambda actually is just 1 over beta, and this lambda is the same lambda as the Poisson lambda. Okay. All right, so I think I give you a list of the things that you need to know about exponential distribution, okay? I'm going to write this here. Things you need to know about exponential distribution. Okay? Okay, the first thing, PDF and the parameters. Okay, the PDF of an exponential distribution. You also need to know that beta, the relationship between beta and lambda. Okay, so the second thing, it characterizes the waiting time between events in a Poisson process. Okay, the third thing, when alpha is equal to 1, so alpha here is the parameter, one of the parameters of gamma distribution. Okay, so you can check this by yourself. So gamma is equivalent to exponential. The gamma distribution is equivalent to exponential distribution when alpha of gamma is equal to 1. Okay, so which means only beta left. So you compare like the PDFs of gamma and exponential, you're gonna find these two are the same. Okay, so also we know that the expectation is equal to beta, variance is equal to beta square. So which means this is equal to 1 over beta, this is equal to 1 over beta square. Okay, and the fifth point, so instead of knowing the CDF in general, like when we learned the previous distributions, we all discussed the CDF of those distributions, right? So the CDF is the probability that x is smaller or equal to small x. But here, like for exponential distribution, we're also interested, or we could say we're more interested in this stuff. Oops. In this stuff, okay? So I can add a equal sign here because it's continuous, so it doesn't matter. Okay, why is that? Because we call this the survival function. Okay, so we would like to know, because we know that x, an exponential random variable characterizes the waiting time between events, right? So basically, you want to know like how long can you live? Can this stuff live, right? So you would like to know the corresponding probability. So this stuff is equal to this or this, right? Okay, the sixth point, memoryless property. Okay, so it says, this is my timeline, all right? Timeline. Okay, so from 0 point, say, okay, so s plus t. So this time is s. This time period is t. Okay, so what does it mean? It means, so the probability that you have to wait for this time long, okay? So this is s plus t, okay? So the probability that you will have to wait for this time long, which is x is larger than s plus t, given that you have already waited for s time, is equal to the probability that you only need to consider, the x is larger than t, which is this period. Okay, so this is the memoryless property. And that's all for the exponential distribution, all right? So 6 things that you need to know about exponential distribution. All right, so that's all for chapter 6. And we have just discussed chapter 8. I also gave you a summary, right? So that's all the things that you need to know. So about the exam, I think I have mentioned in the previous email saying that you have a day to finish it, right? I will upload the exam paper online at 12 a.m. on April the 9th. And then you have to download it and you type all the corresponding answers, including the necessary steps, the necessary formulas. And then you saved it using, your full name, right? As your file name. And then you upload it on Canvas, and the graders will, grade them using Word as well. So please make sure to submit a doc file instead of a photo. Okay, some people say, can I just write in hand, like write on paper and then on a piece of paper and take a photo? Well, it's probably it's easy for you to do this, but it will give the graders a lot of workload, because handwriting is pretty hard to read on screen, and then they cannot like grade it like like conveniently, right? So they have to, if they can do this using Word, like it will be easier. So that's the reason that I would like you to use Word to type it. Okay.